Hello, and welcome to this video on the properties of waves. Amplitude and wavelength first. The amplitude is the maximum displacement of a point in a wave from its undisturbed or equilibrium position. Let's explain what that means by looking at this water surface. At the minute, the water is undisturbed, meaning calm. When waves start to pass by though, some points are higher than they normally would be and others are lower. We call the highest points of a wave the peaks, and the lowest points the troughs. The amplitude can be marked on this diagram as the distance from the undisturbed position to a peak, or from the undisturbed position to a trough. The wavelength of a wave is the distance from a point on one wave to the equivalent point on the wave beside it. The easiest way for us to measure the wavelength of this wave is to measure the distance from a peak to the peak beside it, or from a trough to the next trough over, like this. While amplitude and wavelength are to do with distance, the period and frequency of a wave are to do with time. The period of a wave is the time taken for one complete wave to pass a point, and the frequency is the number of waves passing a point each second. We're going to use this stopwatch to see how many waves pass this point in, say, 3 seconds, so let's go. 1, 2, 3, 4, 5, 6. 6 waves in 3 seconds. That means that each wave took 0.5 seconds to pass, so the period was 0.5 seconds. As for the frequency, because 6 waves passed in 3 seconds, 2 waves must have passed every second, so the frequency was 2 waves per second, though instead of saying 2 per second all the time, we say 2 Hz instead. A frequency of 1 Hz means that one wave is passing a point every second, which means that the source is producing one wave every second. The equation which links the period of a wave to its frequency looks like this. T equals 1 over f. When you're using this equation, if you keep the period in seconds and the frequency in hertz, you won't go wrong. And if it's the kind of thing that floats your boat, here's the formula triangle. Here's a nice easy example to warm you up, starting off with T equals 1 over f, then subbing in that becomes 1 over 50, to give a period of 0.02 seconds. Example 2 is a little trickier. Here, the time has been given in milliseconds. Because 1 millisecond is 0.001 seconds, 5 milliseconds will be 0.005 seconds, so that means that the frequency, which is 1 over t, will be equal to 1 divided by 0.005, which gives an answer of 200 Hz. On to wave speed next, and the wave equation v equals f lambda. Here, v is the speed of the wave in meters per second, f is the frequency in hertz, and the Greek letter lambda is the wavelength in meters. And here's the formula triangle. Let's have a go at this example. Using v equals f lambda, then subbing in that becomes 0.1 times 20 to give a speed of 2 meters per second. This one's a bit trickier because it uses standard form, but it should be doable because we have a value for the wavelength here and a value for the speed, which is here. Rearranging v equals f lambda to make f the subject, we have f equals v over lambda, then subbing in that becomes 3 times 10 to the power of 8 divided by 6.3 times 10 to the power of minus 7, which gives a frequency of 4.8 times 10 to the power of 14 Hz to 1 decimal place. One last wave equation example now, and for part A, we can see that the equilibrium or undisturbed position of the wave is here at a depth of 2 meters. That means that its amplitude must be 1 meter because its maximum displacement is 1 meter above or below this point. For part B, the distance from one peak to the peak beside it is 5 meters, so that means that the wavelength is 5 meters. In part C, we're told that a wave crest, or peak, passes a rock once every 10 seconds. That's another way of saying that the period is 10 seconds, which means that the frequency, which is 1 over t, will be 1 over 10, or 0.1 finally, for part D, we're just using v equals f lambda, then subbing in that becomes 0.1 times 5 to give a speed of 0.5 meters per second. For your exam, you'll have to understand how to measure the speed of, say, a water or sound wave. The steps you need to follow when dealing with one of these questions are always the same. First, you need to measure the distance travelled by the wave and the time taken. Then, you need to plug these values into speed equals distance over time. It sounds pretty straightforward, and it is, but to make sure you don't make any of the mistakes that lots of students make when dealing with speed of sound questions in particular, let's look through a couple of examples. In example 1, as soon as the sound is detected by microphone A, the automatic timer starts. When the sound reaches microphone B, the timer stops. As we can see, the microphones are 2 meters apart, and the time taken for the sound wave to travel from A to B was 6 milliseconds, so the wave speed is given by v equals s over t, then subbing in that becomes 2 over 0.006, which gives an answer of 333 meters per second to the nearest whole number. Have a look through example 2 now. As you can see, the time between the actual bounce and Carol hearing the echo was 0.4 seconds, and the speed of sound is given as 330 meters per second, so let's give it a go. We're going to use two different methods here, so just pick the one you prefer. In method 1, we're going to think about the sound wave travelling all the way to the wall, then all the way back. Our equation again is distance equals speed times time. Here, the distance is actually going to be twice the distance to the wall, and on the right hand side subbing in, we have 330 times 0.4. So 2d equals 132. And the distance to the wall is 66 meters. Method 2 is my personal favourite. Here, we're going to think about the sound wave making a one-way journey from the ball to the wall. The equation again is distance equals speed times time, then subbing in that becomes 330 times 0.2, which was half the total time, which gives an answer of 66 meters, same as before. The required practical for this part of the course involves investigating the properties of the waves in a ripple tank and those in a stretched string. Let's look through each of these in turn. You may have already seen a ripple tank which looks something like this, but if not to worry, there isn't that much to them. The tank itself contains a small amount of water. As the dipper vibrates up and down, it produces waves in the water. These waves can be difficult to see directly, so we normally shine a light through the tank from the top down and look at the image which is formed in the screen below. At the moment, this dipper is producing plane waves. The crests of each of the waves form a series of parallel lines running along the length of the tank, but attachments can be added to it to allow for the production of circular wavefronts instead. To work out the speed at which the waves are travelling, we could measure how long a wave took to cover a given distance and then use speed equals distance over time, but that would probably end up being pretty inaccurate, as these waves tend to be travelling pretty quickly and so the times involved are quite short. A better way to determine the speed of the waves is by using the wave equation v equals f lambda. Remember that the frequency is equal to the number of waves that pass a given point per second, and that their wavelength here can be determined by measuring the distance from one crest to the crest beside it. The way in which we go about taking these measurements and using them to determine the speed of the water waves is illustrated in this example. For part A, we know that the wavelength is equal to the distance from one crest to the crest beside it. We can see that there are 8 wavelengths in a distance of 64 centimeters, so the wavelength is just 64 divided by 8 to give an answer of 8 centimeters, or 0.08 meters. For part B, to work out the frequency of the waves, we just divide the number of waves by the time taken to produce them, or the time they take to pass a given point. So that gives 11 divided by 10, which gives an answer of 1.1 Hertz. Lastly, to work out the speed of the waves, we just use the wave equation, v equals f lambda, then sub in our numbers, 1.1 times 0.08, to give an answer of 0.088 meters per second, or in centimeters per second, 8.8 centimeters per second. The second part of the required practical for this part of the course is on investigating the waves in a stretched string or elastic cord. The most common experimental setup for this investigation looks like this. One end of the string is tied to the vibration generator and the opposite end to the mass hook. The string is held in tension by the weight of the masses and is forced into oscillation between the vibration generator and the bridge. By either adjusting the frequency at which the vibration generator is vibrating, or by adjusting the position of the bridge along the string, we can end up with a really pretty wave pattern which might look something like this. This pattern, which is called a standing wave, is produced due to the interaction between the wave which is travelling away from the vibration generator and that which is reflected from the bridge and is travelling in the opposite direction. This equation allows us to work out the wavelength of one of these waves. Here, for example, there are 10 loops on the string. If the total length of string between the vibration generator and bridge is 1 meter, then the wavelength will be equal to 1 divided by 10 times 2, or 0.2 meters. The frequency of the waves can be determined by looking at the setting on the signal generator which is connected to the vibration generator. From there, it's again just a matter of using v equals f lambda to work out the speed at which the waves are travelling, but I'll leave that bit of fun for the exam style questions. One of the factors which affects the speed of the waves in the string is the tension in it. Could you design an experiment to investigate how the speed of these waves was affected by the number of masses attached to the end of the string? This last little physics-only section is on what happens when waves travel from one medium into another. A medium is just the material that the wave is travelling through, like air, water, glass, or empty space. Before going any further though, we need to learn about wavefront diagrams. Here, we're looking at a water wave side on and can see all of its peaks and troughs in all their glory. To represent the same wave top down, we need to use a wavefront diagram like this. Here, each of the black lines represents one of the peaks of the wave above. Wavefront diagrams are useful because they allow us to see very easily whether the wavelength of a wave is getting shorter, longer, or staying the same. When waves travel from one medium into another, their frequency stays the same. Let's look at what happens when a water wave travels from deep water into shallow water. Although the frequency of the waves is the same in the shallow water, we can see that the wavelength is shorter. This is because water waves travel more slowly in shallower water, which causes the wavefronts to bunch up, or in other words, causes the wavelength to decrease. From the wave equation, we can see that because the frequency of a wave is constant when it travels from one medium into another, the wave speed and wavelength must be proportional to one another. Doubling v causes lambda to double, halving v causes lambda to half, and so on. One last example now to see you on your way. The key thing to remember here is that the frequency of the sound wave produced by the earthquake doesn't change when it moves from water into air. We're told that the wavelength of the wave in water is 30 meters and that the speed in water is 1500 meters per second. Rearranging v equals f lambda, we have f equals v divided by lambda, then subbing in. That becomes 1500 divided by 30 to give a frequency of 50 Hz. So now that we know the speed of the sound wave in air and the frequency, to work out the wavelength, we just use lambda equals v divided by f, then subbing in that becomes 330 divided by 50, which gives 6.6 meters. That brings us to the end of this important video on the properties of waves, but to learn this topic properly, you should test yourself with a few of the exam style questions. Thanks for watching and good luck.